First question we've got has to do with scientific notation. So they've given us a few numbers here and they want us to convert these over to scientific notation. The way these are written right now is just called standard notation. So it's just the normal way that you'd write a number. So the way we need to do this is we need to move that decimal place over a certain amount of spots. So what the scientific notation is going to look like for this first one is we're going to write this as 6.5 times 10 to the power of something. So we've got to write some number up there for the power of 10. And to figure that out, what number that is, we've got to count how many places we just moved that decimal. So the decimal started over here, and then it ended up over there. So we went 1, 2, 3, 4, 5, 6. So we moved that decimal place 6 places. So that's going to be 6.5 times 10 to the power of 6. Then we can do the same thing for the second one. We're going to include as many numbers as we need to past the decimal so that we don't lose any information. So we're going to write this as 8.023. The rest of them are just zeros, so we can stop there. And then we can go times 10, and then we got to count again. So they've grouped up these numbers here so it's a little bit easier to count. We can go 3, 6, 7, 8, 9. So that will be 10 to the power of 9. Okay, then we can move on to the next ones here. So for C, we've got 0.91. So we just need to move that decimal place 1 over. But this time we're moving the decimal to the right instead of going to the left. So what that's going to look like is 9.1 times 10 to the power of -1. Same thing for D. We've got a really tiny number here, so we've got to make this bigger. So we've got to move the decimal to the right by a whole bunch. So we've got to go 3 times 10, and then same thing here, we can count up how many spaces we're moving to the right. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's going to be 3 times 10 to the -9. So the thing that I always try to remember here is that when you look at the exponents, some of them are positive and some of them are negative. The positive exponents, that means that those are really big numbers that we're working with. So you can see from A and B, those numbers were huge. We're able to make them a lot smaller by writing them in scientific notation. If we've got a negative exponent, like for D, for example, that one has a negative exponent, that means that we're working with a really tiny number. So the way that you can kind of think of this is this scientific notation is we're either multiplying by 10 or dividing by 10. In these ones here, this is like times 10, but you're doing it 6 times. So 10 times 10 times 10, 6 times. This one is sort of like you're dividing by 10, but you're doing it over and over again. So if you take 3 and you divide it by 10 9 times, you'll end up with this number. The other thing to keep in mind here is that most calculators can do this for you, so you don't have to do a lot of this by hand, but it's good to practice these by hand at first just to get a feel for how it works. Okay, so the next question is the same thing, but we're doing the exact opposite. We are writing the numbers in standard notation when they gave us scientific notation. So this is where the big and small numbers thing is handy because we need to figure out which way we're moving this decimal. So for the first one, we've got a negative exponent. So it's going to be 0.000, a bunch of zeros, and then 65 at the end. Should be a really small number because we have a negative exponent. So these ones are a little bit tricky to work out. I usually just kind of guess and then check to make sure that I got this right. So 0.00006. And then just count to make sure we got this right. So 1, 2, 3, 4, 5 spots. Yep, we're okay. That should be good. Then for B, we've got a positive exponent for this one, so it's going to be sort of the opposite. We're going to be 2, 1, and then a whole bunch of zeros. So if we just write 2, 1, 21, we've moved the decimal place over by 1. So this number is 8 here, so we've already taken care of 1 decimal place. We've got 7 more to go. So that means we're going to need 7 zeros. So 1, 2, 3, 4, 5, 6, 7. And then again, we can double check and make sure that's right. So 1, 2, 3, 4, 5, 6, 7, 8. Yeah, it looks like we're good. Okay, for C, 1.0 times 10 to the 5, that's going to be 1, and then 5 zeros. 1, 2, 3, 4, 5. D, this one's going to be huge, but kind of using the same logic here, I'm going to go 3.01, sorry, we're going to go 301, and we've already moved over 2 decimal places, so we've got 11 more to go, so that means we need 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so you can see why, from this last one, why scientific notation is used, is because it gets really tedious if you're doing a bunch of calculations with big numbers, or really small numbers, to keep writing these zeros out over and over and over again. It's really easy to make a mistake. So instead of doing it like that, we just switch it over to scientific notation. It makes it a lot faster to do those calculations. Okay, so now we're moving on to how to actually do some calculations when we have scientific notation. So the way that I usually think about this, and again, you can plug this whole thing in your calculator and it'll just do everything for you, but I would recommend doing it by hand first and just making sure that you can get the right answers here. So we've got 4 times 10 to the negative 3 times negative 5 times 10 to the minus 5. So the way I usually think of this is to just kind of split it up and put the 2 numbers out front. So because this is multiplication, we can write this in any order. So I'm going to go 4 times negative 5, and that gives me negative 20. And then I'm going to go 10 to the negative 3 times 10 to the negative 5. When you do that, and they both have the same base, we're just going to add those 2 exponents. So it's going to be 10 to the negative 8. So the number that we should end up with here is minus 20 times 10 to the negative 8. But we're not quite in scientific notation yet because our decimal place is right there, and we want our decimal to be right there. So we've got to shuffle it over by 1 spot. So we're going to move this decimal place this way by 1 to change this to minus 2. And then when we do that, we've got to shuffle this over a little bit as well. So what we just did is we took 20, and to change it to 2, we have to divide it by 10. So to balance this out and make sure we're not changing anything, we've got to multiply this number by 10 or increase this counter by 1. So we're going to add 1 to that counter, which is going to turn into negative 7. Again, all can be done on the calculator. If you just plug that in, it should just give you this number if you have your calculator set up properly. But good to practice these at the beginning just to see how it works. Okay, for part B, same sort of deal here. We've got 8 times 1.2. We can calculate that. We'll get 9.6. And then 10 to the 5 times 10 to the 8. We'll add 5 and 8 to get 10 to the power of 13. So our answer here should be 9.6 times 10 to the power of 13. This one, the decimal is already in the right place, so we don't have to worry about shuffling that decimal around. So we can just leave our answer like that, and we'll be good to go. Okay, question C. Now instead of multiplying, we are dividing these. So let's write this out a little different. Let's go 2.3 times 10 to the negative 3, and then let's write our divided like this. 1.0 times 10 to the minus 5. Okay, now this looks confusing, but it's actually not too bad. So if we just look at the 2 numbers that are out front, this is basically just 2.3 divided by 1. And if we're dividing by 1, it's not going to change our number at all. So that should just be equal to 2.3. We can just leave that part the way it is. Then let's divide these 2 numbers. So if we're dividing, then we should be subtracting the exponents. So I'm going to write this out in 2 steps here to make sure we got this right. It would be minus 3, and then we're subtracting negative 5. So subtracting negative 5 is going to be like the same thing as if we're just adding 5. Negative 3 plus 5 is going to give us positive 2. So we can write it like that, 2.3 times 10 to the power of 2. Okay, D, same thing, another division here, but a little bit harder. So we've got 8 times 10 to the 5 divided by 1.2 times 10 to the 8. Okay, so this one we're going to need a calculator here probably to help us out a little bit. But if we divide those two numbers, we should get 7 for 8 divided by 1.2. And then we can do the same thing over here. We can go 10 to the 5 divided by 10 to the 8 is going to be 10 to the power of 5 minus 8, which is negative 3. So we'll end up with 7 times 10 to the power of negative 3 for that one. Okay, the next one we have is we're doing an exponent for this last one, or this next one. So we're raising this to the power of 2. So let's go like this. We've got 3 times 10 to the power of 8, and the whole thing is squared. So we could write this, we could split this up. We could go 3 times 10 to the power of 8 times 3 times 10 to the power of 8. We already know how to deal with that. We take the two numbers that are not the 10s and multiply those together. 3 times 3 gives us 9, and then 10 to the 8 times 10 to the 8, we're going to add those two exponents together, so we'll get 10 to the power of 16. The other shortcut that you could do here is you can multiply those two numbers together, and that will give you 16 as well. So a couple different ways to do it. Okay, let's do f next. So this one is a square root. We've got the square root of 4 times 10 to the power of 8. So again, we can kind of split this up. We can do the square root of 4, which is equal to 2. And then the square root of 10 to the power of 8, we could write that square root as a fraction instead of a square root. So we could write it like this, to the power of 1/2. So square root is the same thing as taking the power of 1/2. And then if we use that little trick that we just learned before where we multiply those two numbers together, 8 times 1/2 gives us 4. So we can write 10 to the power of 4. Okay, the last one here is g. Let's clear off some space. This one's a big one, but we can split this all up here, which should make this a little bit easier. This one probably, if I was doing this, I would just fire this into the calculator, but let's write this out and see what we got. 3.27 times 10 to the 24, 9.63 times 10 to the 14, all divided by all this. 9.345 times 10 to the 4, 8.63 times 10 to the negative 9. Okay, so now with this one, I would definitely recommend just firing this into the calculator. This will be a good practice so that you can make sure the calculator, you know how to use it properly. If we do that, we should get 3.90 times 10 to the power of 42. So you can plug that into your calculator to make sure that you're able to do that properly. Okay, next up we're moving on to significant figures. So this is a really important part for physics, especially for the labs. This shows up over and over again. So significant figures has to do with how confident we are in the numbers that we're providing. So in the labs, a lot of the time we're taking measurements of numbers, and the significant figures kind of gives us an idea or a feel for how confident we are in the numbers that we're measuring. So the more significant figures we include, it sort of implies that we're really confident in that number that we're providing. Whereas if you have just a couple significant figures, it's sort of like a rough measurement, a rough estimate. So to count the significant figures, start with the first one. The first one has 4 numbers. There's no decimals and there's no zeros in there, so that is an easy 4. For the second one, we have 3 numbers and there's a decimal, but there's no zeros in this number. So again, we just count all of those numbers. We've got 3 digits in there, so we've got 3. Question C, same thing. We've got a decimal, but we have two numbers and none of them are zeros, so that's a 2. So the rule here is that if there's no zeros, we can count all of the numbers, all of the digits as significant figures. If there is zeros in here, then we've got to do some more thinking. So for D, there's a 0, but the 0 is in the middle between two non-zero digits, so that still counts as a significant figure. So that's going to be 3. Okay, now we get to one that's more exciting. So if we look at E, we've got 1, 2, 3, 4, 5, 6 different digits. 2 zeros there are captured in between the 1 and the 2. So we're going to have to include those numbers. But the 0 out front, in front of the decimal, doesn't count. We have to put that 0 there so that we know that this is a decimal, but it doesn't actually give us any extra information, so we've got to exclude that one. So that is going to just be 5 significant figures. Okay, so then for this next one, for 500, we've got 3 different digits. 2 of them are zeros, but there's no non-zero digit on the right side. So that means that we can exclude the 2 numbers on the right, the 2 zeros. And so the only significant digit that we have here is the 5. So there's just one significant figure. So basically what this means is you took some measurement. Let's say you measured something and you said it's about 500 meters. It means that it could be a little bit higher than 500, could be a little bit lower than 500, but we know that it's approximately 500. If I said that measurement was 514 meters, then that's a little bit more accurate, so we'd have to include those 3 significant figures. So the same deal with G. This next measurement that we have is 5 and a whole bunch of zeros after it. So all of those zeros do not count. The only one that counts is the one at the very beginning, the 5. So again, we have one significant figure. Now for this next one, we're missing a piece here, so let me fix this up. There should be a little 0 at the end of this. This is the one that's different, and this is the one that always gets people. If I said my measurement was 500, like in F, I would have to say that that's one significant figure. But in H, I've included these extra zeros as the decimal at the very end. So since I'm saying it's 500.0, I have to include all of those numbers, because I could have just left the 0 off here. If I left the 0 off, it would have been one significant figure, but I kept it in there. So that means that we're working with 4 significant figures for this one. Okay, so question I, we've got a whole bunch of zeros and then 2 non-zero digits. Those are the only 2 that count here. These zeros, we can't write this number without including those zeros in here. We have to put them in there. But there's 0 and there's no number on the left, which is not 0. So that means we have to only include the 2 and the 7. For this next one, we could have written this number like this. We could have just written it 0.6. That's the same number. If we had written it like this, it would have just been one significant figure. But since we chose to include all those extra zeros in there, we've got to count those all up, and those all count. So 1, 2, 3, 4, 5, 6. That means we're going to have 6 significant figures. Same with this one down here. Sorry, we're on K. We're always on this one here. So this is scientific notation. You can do the same thing here. There's a 0, but it's in between 2 numbers, so we've got to include it. We've got 3 significant figures. 1, 2, 3. With this next one over here, this 1.00, we chose to include those 2 zeros in there. We could have written the number like this, 1 times 10 to the negative 4, and that would have had one significant figure. We didn't have to include those zeros, but we chose to. So that means we should include those as significant figures, and that would be 3. Same with M. We could have written this number and not had all these zeros at the end, but we decided to include them in there. So that means that we've got to include those in our significant figures, and we count up to the 8. Everything on the left, we have to include those zeros, the ones over here, so those ones don't count. So if we count these up, we got 1, 2, 3, 4, 5, 6, 7. Okay, so moving on to doing some calculations and writing our answers with the correct number of sig figs. So what's going to happen here is we're going to do some calculations, and then we have to round our answer so that it matches the right number of sig figs. So the first thing we can do is just do this calculation. So if we plug this into our calculator, 16.13 plus 10.764 plus 4.5, plug that in the calculator and we get 31.394. Okay, so now what we've got to do is take a look at the significant figures that we started with in the problem for all these different numbers. And the other thing we have to check is whether we're doing multiplication or division, because the rules here are a little bit different. Okay, so for adding and subtracting, we look at the decimal place. So we look at kind of the one that has the worst amount of precision. So this one has 2 decimal places, that one's got 3 decimal places, and this one's only got 1 decimal. So that means that we're going to round it to the same as whatever the worst precision is, which is 1 decimal. So we're going to round that to 31, and we're going to round the 3 up to 4 because this 9 is closer to 10 than it is to 0. So we're going to round that to 31.4. Okay, so now for B, we can do this division here first. So let me plug this in the calculator. 13.72 divided by 0.0004. And if we write this number out, we get 34300 as our answer. But now we're doing dividing. So now the significant figures becomes important. So now we're not looking at the decimal places, we're counting significant figures. The first one has 4 significant figures. The second one has 2 significant figures. We go with whichever is the lower number of sig figs. So the lower out of 4 and 2 is 2. So we're going to round this to 34000. Okay, for C, we've moved on. We're doing back to addition over here. So again, put this part with the calculator first. 118.65. We're doing addition, so we got to look at precision. The first number on here has 0 decimals. We've got 2 decimals there and 1 decimal there. So the 0 decimals is the worst precision. So we're going to round this to no decimal places. So we're going to round this to 119. Okay, now we got multiplication over here. So we can do that multiplication. 50 times 3.21, 160.5. Then we've got to look at sig figs because we are doing multiplication again. So we've got 1 sig fig for the 50 and 3 sig figs for the 3.21. So we're going to have to round this number to 1 sig fig. So when you're doing this at first, it feels uncomfortable because you're rounding this very extreme amount. So we're going to round this to 200. That's what we have to do. So it seems wrong because we had 160.5. It's pretty, accurate answer, and we just rounded this to 200. But that's the way that we have to do this to make sure that we got the right number of sig figs. We only had 1 to start, so we've got to have 1 in our answer as well. Okay, we've got a couple more, division and multiplication. So for E, I'm going to put this in the calculator. That gives us 400 as an answer. Now we're doing division again, so we've got to count significant figures. The first number up top has 3 significant figures, and the second one has 2. So we go with what's worse, which is 2. And we've already kind of got that here. But to write this, they didn't really tell us what to do here, but to do this a little better, let's write this in scientific notation because I think that will make this work a little better. Because we want to show those 2 significant figures, we can't really round this one to 2 sig figs. So let's go two significant figures in scientific notation would be 4.0, and we've got to times that by 10 twice to get to 400. So times 10 to the power of 2. Then for f, we got the same thing except multiplication this time, so let me plug this one into the calculator. .2048. So same deal with this one. Let's convert this over to scientific notation with the right number of sig figs. We have 2 here, and we have 3 over here, so we're going to go with 2. So we're going to write that as 2.0 times 10 to the power of 3. Okay. Next up, we got unit conversion. So this is super important for all of physics. My background's in mechanical engineering, and I use this all the time for pretty much every engineering course. Nearly every question had some sort of unit conversions in here. So I'm going to show you guys how I like to do these unit conversions. So I like to write these out with kind of a little bit of extra steps. At the beginning, it's going to seem like a little bit of overkill, but it really does make it easier, especially when the unit conversions start to get really challenging. So I'll show you how I like to do this. We got 5 kilograms, and we want to convert that over to grams. So I like to write it out like this. I like to set up, there's going to be a fraction here, and I always start with the symbols first and then figure out the numbers after. So we've got kilograms on the top of our fraction, and we want to get rid of kilograms. So to cancel those out, we need to have kilograms on the bottom. We want to end up with grams, so we're going to put grams on the top. Now, this is helpful if you have a big list of unit conversions in front of you. We need to know how many grams are in a kilogram or how many kilograms in a gram. In this case, if we look at our sheet here, we can see that 1 kilogram is 1,000 grams. Now, I always like to check and make sure that this cancels out nicely, so kilograms is going to cancel. We're going to be left with grams, which is what we want. So to multiply this out, we just need to go 5 times 1,000 divided by 1, which doesn't change our answer, and gives us 5,000 grams. When you're working with units, you always have to write the symbol next to it. So if you just write 5,000, a lot of teachers will mark it wrong because it's a little bit vague. So we need to put the G next to it to say that we've converted that over to grams. Okay, next up we're converting meters to kilometers. So same thing, we can go 8, 7, 6, 5 meters. We want to get rid of meters and we want kilometers. So we'll put meters on the bottom, kilometers on top. 1 kilometer is 1,000 meters. Double check we got this right. Meters cancels with meters. We're left with kilometers. Okay, that looks good. Then we can go and do this calculation. So this will be 8,765 divided by 1,000, which is going to be 8.765 kilometers. Okay, next up we've got grams to kilograms. So we go 560 grams. And same thing, we want kilograms up top this time, and we want to get rid of grams. So now our numbers are going to be flipped around. We're going to have the 1 up top and the 1,000 on the bottom, because 1 kilogram is 1,000 grams. And then when we calculate this, we should get 0.560 kilograms. Okay, next up we got kilometers to meters. So 25 kilometers. Kilometers on the bottom to cancel them out. Meters up top because that's what we want. 1 kilometer is 1,000 meters. So cancel our kilometers and we're left with meters. And we've got 25,000 meters. Okay, so next for E, we're going minutes to seconds. So we got 59.2 minutes. And we want to convert that over to seconds. So we want seconds up top, minutes on the bottom. every 1 minute is 60 seconds. So we just got to multiply that number by 60 to get our answer. I'm going to do that in the calculator here. 3,552 seconds. Okay, now we're going the other way, and we're going from seconds to minutes. So for the next one, we've got 87 seconds, and we want to convert that over to minutes. So it's going to look upside down here from what we just did last time. So now we're going to put seconds on the bottom, minutes up top. 1 minute is 60 seconds. So we're going to take 87 and divide it by 60 in the calculator to give us 1.45 minutes. Okay, next up we got some speeds that we're working with here. So we're going to go with kilometers per hour to meters per second. So this is going to be really common in the next section when we do kinematics. We're going to be doing this calculation over and over again, so it's pretty handy. To write this out, I like to go like this. So I like to go 25 kilometers, and instead of writing it kind of in line with the slash, I like to write it stacked. So kilometers per hour, because now this is going to work a little better with the way we've set up our notation. So let's deal with the kilometers first. Let's put the kilometers on the bottom. We want this to be meters, so we're going to convert kilometers to meters. 1 kilometer, 1,000 meters. Okay, so that part's taken care of, but now if we just plug this in into our calculator, we would get meters per hour, and we want meters per second. So we've got to just stack these unit conversions on top of each other. We can go from hours to minutes. So put the hours on top so it cancels. 1 hour is 60 minutes, and then we got to do one more here to get to seconds. So we want to get rid of minutes. We want seconds on the bottom. 1 minute is 60 seconds. Now we can go back and check and make sure this is all good. Hours cancels with hours, minutes cancels with minutes. Okay, now we've got what's left over, which is meters per second, so that looks good. Now to plug this into the calculator, we've got to go 25 times 1,000 divided by 60 divided by 60. And that should give us 6.94 meters per second. Okay, so now we're going to do the same thing, but we're going to go in the exact opposite order. So we're going to go from meters per second to kilometers per hour. So let's try that again, going the other way. So you got 120 meters per second. Okay, so let's get the kilometers in there first. Let's put meters on the bottom, kilometers up top, and we want 1 kilometer, 1,000 meters. Okay, and then we got to go seconds to minutes. So let's put the seconds on top, minutes on the bottom. 1 minute, 60 seconds. And then let's go minutes to hours. So we got minutes up here, hours on the bottom. 1 hour, 60 minutes. Now let's double check, make sure we got this right. Meters cancels with meters. Seconds cancels with seconds. Minutes cancels with minutes. And we're left with kilometers per hour. So now to plug this in the calculator, I'm going to go 120 divided by 1,000 times 60 times 60. And that gives me 432 kilometers per hour. Okay, next up we got some more unit conversions. So with this one, these ones are a little bit more less commonly used, I guess. Some of these are kind of some weird ones in here. Some of these are common, meters to centimeters, centimeters to millimeters. We're going to use those all the time. Depending on what kind of physics you're doing, the micrometers might be helpful as well. There's also a couple weird ones in here that are not that common. But the way to sort this out is if you look up a table for common prefixes used with SI units, you'll bring up this table, and that table will give you all the different unit conversions that you need based on what is the little symbol in front of our meters here. So what I mean by that is when we go to this first one and we do 37 meters to centimeters, 37 meters, and we want to convert that to centimeters. We're going to put meters on the bottom, centimeters up top. Then you can look at the table and it'll tell you what numbers you need to put in here. So for centi, that's going to be 100 centimeters for 1 meter. So when we plug this in, we get 3700 centimeters. Now we're going to go from meters to millimeters. So 7 meters. Looking at the table again, we'll get our numbers that we need for this. So meters on the bottom, 1 meter is 1,000, so milli is 1,000. Then our meters are going to cancel, we'll be left with millimeters. We go 7,000 millimeters. Okay, now we're going from centimeters to millimeters. And I'm going to show you the way that I would probably recommend doing these ones. Is, especially when you're first learning here, this is really easy to get mixed up with what the units are. So of course you can go from centimeters directly to millimeters, but it becomes a lot to remember, and this gets really hard, especially when you're going between really weird units. You'll see this when we get down to some of the later ones. That usually the easier way to do this is just to go back to meters first, and then go from meters to millimeters. So the first thing that I'm going to do is I'm going to go from centimeters to meters. 1 meter is 100 centimeters. And then we're going to go from meters to millimeters. 1 meter is 1,000 millimeters. So if we look at what we've got here, we can plug this all in the calculator and then we can get our answer. 470 millimeters. Now for that one, centimeters to millimeters, you might have just said, oh, well, I know there's 10 millimeters in 1 centimeter, so I can just multiply this by 10. That's also totally okay for that one. When it gets harder, it gets pretty hard to do that. So I find the less that you can remember, the easier that this is. So instead of trying to remember all the different intermediate ones, if we know how to get back to meters, and we know how to get from meters to anywhere, then it just becomes a little bit easier to manage. Alright, D, we've got 47 centimeters over to meters. So centimeters bottom, meters up top. 1 meter is 100. Calculate that, 0.47 meters. Okay, so for question E, we've got a weird one, H, which is, this is one of the ones that is not super common. So our H is hecto, and this is where the table comes in handy. We've got 5 hectometers, converting this over to centimeters. So again, I'm going to do the same thing where I go hecto back to the base unit here, and hecto is kind of like centi, but in the opposite direction. So we're going to go hectometer back to meters, and we're going to work this out so that 1 hectometer is 100 meters. So it's still a factor of 100, just like centimeter, but it goes the other way. And then we're going to go from meters to centimeters. So we're going to get rid of meters, we want centimeters. 1 meter is 100 centimeters, so we're going to be multiplying this by 100 twice. So it'll be 50000. Okay, the next one, micrometers. This one's a really, really tiny measurement, and we're going to go to centimeters. So same thing with this, I'm going to go back to meters first, and then I'm going to go to centimeters. Okay, so for this one, when the numbers start to get really small, it gets a little bit tedious writing all these zeros over and over again. So I'm going to use scientific notation to make this a little bit easier to work with. So I want meters, I want to get rid of micrometers, and what I'm going to do is I'm going to say 1 meter is 10 to the power of 6 micrometers. Then I'm going to go from meters to centimeters. That's our last step here. So meters to centimeters, we can go get rid of the meters, centimeters up top. 1 meter is 100 centimeters. And then we can plug this into our calculator as well to get our answer. So 18 divided by 10 to the power of 6 times 100 is going to give us 1.8 times 10 to the negative 3. And that's just how my calculator spat out that answer. If you have a different calculator, it might tell you a bunch of decimals in there. That's okay as well. Okay, we just got one more here, hectometer to kilometer. So let's write this out again. Let's go to meters first, and then from meters we'll go to kilometers. Okay, so looking at our table again, we got hectometers we want to get rid of, meters we want. We said that 1 hectometer is 100 meters, and then we want to go to kilometers, so we can get rid of meters, put our kilometers in, and we know that 1 kilometer is 1,000 meters. So when we plug this in, we're timesing by 100, and then we're dividing by 1,000, so it's like the same thing as dividing by 10 if we cancel those out. And if we do that, we should be at 1.8 kilometers. Okay. How many minutes are in 7 years? And how many seconds are there in a billion years? Okay, let's start with the first one. How many minutes are in 7 years? So we're going to take 7 years, and we're just going to start doing a whole bunch of unit conversions. So we want years, we want to convert that over to days. So let's get rid of years. Let's put in days up top. So we got 1 year is 365 days. Okay, so our years are canceled. We're left with days when we do that. Now we want to get to minutes, so we got to keep breaking this down. Let's go to days to hours. So we know that 1 day is 24 hours. Then we want to go to minutes, so we got to go hours to minutes. So we'll put hours on the bottom, minutes up top. We got 1 hour is 60 minutes, and then let's go back and check and make sure this works. We've got days, canceling with days, hours and hours, so we should be left with minutes. So now when we go and plug this in, it's going to be 7 times 365 times 24 times 60, which gives us a big number. 3679200 minutes. Okay, so that's our answer for that part. How many seconds are there in a billion years? We're actually going to reuse most of what we just did here, so let me just modify this a little bit. So let's keep most of what we've done here. Let's just go back and edit this a little bit. So let's change this to question B. Instead of 7 years, we need a billion. So let's write out a billion here first of all. So a billion, it's going to be 1, 0, 0, 0 for our millions, 0, 0, 0 for our thousands, and then 0, 0, 0. So that's what our number is going to look like for a billion. I'm going to make this a little bit easier for myself and write this as scientific notation. I'm going to go 1 times 10 to the power of 369. Okay, so 1 billion is the same as 1 times 10 to the power of 9. So I'm going to write that as right here. So 10 to the power of 9. I'm going to get rid of the 1 there because it doesn't really make a difference here. It's just 1 times anything is the same number. Now to sort this out, we've got to go one step further, and we've got minutes right now is what we left off with. Let me cancel these out again. These are gone. Those are gone. We just need to go to seconds. So I'm kind of reusing what we did last time here. And we're going to go minutes, seconds. 1 minute is 60 seconds. Okay, now I'm going to try and fire this in the calculator, and we're going to see what this gives me here. It's going to be a really big number. So we got 10 to the power of 9 times 365 times 24 times 60 times 60. And when we plug that in, we get 3.1536 times 10 to the power of 16. is in seconds. Okay, that's what they got as well, so I think we're good there. Alright, so moving on to some more lab-related stuff. So this question, Susan measured the length of her desk to be 1.7 meters, but the actual length is 1.9 meters. So the way we can calculate this is we can take the difference between those two numbers. 1.9 minus 1.7, plug that in the calculator, gives us 0.2 meters. Then we want to take this absolute error and calculate the percent error. So the absolute error, that includes our units in there. So that tells us that our measurement was 0.2 meters off of what the actual length is, but the percentage error gives us a relative amount. So to convert this over to a percent, we just got to take that absolute error, 0.2 meters, divide it by the actual length, 1.9 meters, and then times that by 100%. Now we can plug that in the calculator to see what we get. Okay, and if we do that, we get about 10.5%. So the percent error is nice because it gives us a better feel for the number. If I just told you that we took a measurement and we were 0.2 meters off, that number doesn't give me a lot of information because I don't know how big the original measurement was. If I'm measuring something that's 100 meters long, 0.2 meters off is pretty good. But in this case, the desk is 1.7 meters and the actual length, the measurement was 1.7 meters and the actual length is 1.9 meters. That 0.2 meters is pretty big. If you just give the percent, it's a little bit easier to get a feel for it. You can say, we're about 10.5% off of that measurement. So that's a little bit easier to interpret that number. Okay, same deal with this one. What's our absolute error in the measurement? We're just going to take the difference between those two numbers. So for the first part, 3.5 divided by, minus 3.2 gives us 0.3 kilograms. Then to find the percent error in that calculation, we're going to take the absolute error, divide it by the actual mass, 3.2, and then multiply it by 100%. So 0.3 divided by 3.2 times 100% gives us about 9.375. So let's go 9.4. So we're about 9.4%. Okay, last question from this section is, we've got an iPod which has been put the password in wrong a number of times, and iPod's disabled, try again in that many minutes. We got this big number. So we want to figure out how many seconds until I can try again to unlock my iPod. So for the first part, let's convert this over to seconds. We've got 2, 2, 2, 3, 6, 3, 9, 0 minutes. Okay, so we're going to convert this over to seconds. Let's go like this. Let's put minutes on the bottom, seconds up top. 1 minute is 60 seconds. So we're going to take that big number and multiply it by 60 to get an even bigger number. And I might even convert this to scientific notation because it's just a huge number. So 1.334 approximately. There's a bunch more decimals in there, but we'll just leave it like this. 1.334 times 10 to the 9 seconds. So an absolutely huge number. Okay, how many days until I can try to unlock my iPod? So let's start with the minutes because that's closer to days than seconds. And then we'll go from minutes to days. 2, 2, 2, 3, 6, 3, 9, 0 minutes. So let's go to hours first, minutes to hours. And then from hours to days. Okay, so we're going to take that big number again. We're going to divide it by 60 to get it into minutes. Sorry, to get it from minutes to hours. Then we're going to divide it by 24 to get it into days, which is 15442, approximately, rounding that there, days. So this is a long time. Let's go to the next part where we're converting this to weeks. So we're going to take the answer from the part that we just did and then use that to get to weeks. So we got 15442 days, and we got 7 days per week. So we're going to put days on the bottom, weeks up top, 1 week, 7 days. So we can take that number, divide it by 7. Still a big number, 2206 approximately weeks. Okay, now the last one is how many years. So now we've got to go weeks to years. So let's go part D. We're going to take that 2206 weeks and convert that over to years. So we've got weeks on the bottom, years up top. 1 year is 52 weeks. So we can take that number and divide it by 52, which gives us about 42.4. Might be a bit of round off error in that calculation, but that's okay. That gives us our final answer. So this number in minutes works out to this many years. Okay, so for this first question, we've got some information that they gave us, and they just want us to solve for the time. So the information they gave us was our final velocity, initial velocity, and our acceleration. So what I'm going to do is I'm going to write these down here in the corner for our kinematics equations, and then we can use those when we go and solve these to figure out which equation we want to use. So I'll put these up here. So these are the equations that we have to work with. So we have final velocity is initial velocity plus acceleration times time. We've got this one with the final velocity squared. Now if you're looking at these on your formula sheet, they will probably look a little different. They look different on everyone's sheets. There's a couple different ways that you can write all these things on here. I'll try and explain some of the differences here once we've got these all written out. But what I would always recommend is to use the formula sheet that your teacher gave you if you're enrolled in the class and you're learning this through a class, because that's probably what you'll have access to on the test, so you'll get used to your own formula sheet. Okay, so let's think about what we've got here. So we've got 4 different equations, and we have to pick which one is going to work for us. So if we look at all the stuff that was given here, they told us we know the final velocity, we know the initial velocity, we know our acceleration, and we want to find time. There was no mention of displacement in our equations. So that means that when we look through this list, we want to exclude any of the ones that have displacement in them. So that's going to be this one, and this one, and that leaves us with the first one. So it's an easy way to tell which equation you want to use, is just to look for what you don't have and what you don't want, and try and find an equation which does not include that. So we can start with that first equation. Velocity final is equal to initial plus acceleration times time. Now we want to solve this for time. So to do that, we've got to take that initial velocity over to the left side of the equation, and we've got to subtract it. So we'll get final velocity minus initial velocity is equal to acceleration times time. And then to get the time all by itself, we're going to divide by acceleration. So we'll divide both sides by acceleration, and we'll get v final minus v initial over acceleration is equal to time. So that'll be our equation that we can work with to start us off here. Now we just need to plug in our numbers. If we look at all the numbers, everything is in our at normal SI units, so we don't have kilometers or hours or anything like that, so we can just go ahead and plug this in. We've got 36.8 as the final, minus the initial, 53.2, divided by acceleration, which is negative 2.5. Now I'll plug that into my calculator, and that will give us the time that it would take to change our speed like that, given that acceleration. Alright, so I plug that in and I get 6.56 seconds. Something I'll quickly mention here with regards to sig figs is some teachers are quite picky about this and some are not. So just kind of ask your teacher and just make sure that you're doing it the way that they want you to do this. What some teachers would do is they would say, look at the question and look at the number of sig figs and then write your answer with the same number of sig figs. So they might say 3 sig figs, 3 sig figs, 2 sig figs. So they might want you to round your answer to 6.6 seconds. Some teachers don't do that though, so if your teacher doesn't do that, then don't worry about it and just leave whatever amount of decimals feels right to you. Okay, so similar to the last one, they're giving us some information and asking us to solve for some unknown information. They use D here, which is pretty common for Physics 11. On the formulas that I've got referenced here, they've written this as delta x. They both mean the displacement in this case, so they are interchangeable for the purposes of this. So we can look at our equations and the list that we have here, and then we can try and figure out which one we want to use. So the thing that we were not given here and that we don't care about is time. So if we look at those 4 equations, there's only one which does not include time, which is this one. So the one with the squares. Okay, now we're trying to solve for initial velocity. So we've got to take all these terms and bring them over to the left side. So final velocity squared minus 2a delta x is equal to our initial velocity squared. And then to get that squared, we want to get rid of that. We have to square root both sides. So that's going to be the square root of all of this stuff. V final squared minus 2a delta x is equal to V initial. Now we can go ahead and plug in our numbers here. And just checking our units to make sure we're in SI units again. Yes, yes, all good. So we can just go ahead and plug those numbers in. So the final velocity squared was 45 minus 2 times the acceleration, which was 2.8. And our delta x, or d in this case, is 132 meters. So let's go and plug that in. So we're just plugging that into the calculator. And we get 35.9, let's say. Okay, as I'm going through, just checking my answers here as well. Looks good. That's what they got. I think we're good. All right, same style of question. What we don't have here and what we don't want is the time. So that means we're going to use the same equation. So V final squared is equal to V initial squared plus 2a delta x. And this time we're solving for the acceleration. So when we do our algebra and we rearrange this, it's going to look a little different. Now we want to bring the initial velocity over to the other side. So that's going to be minus initial velocity. And then to get the a by itself, we've got to divide by 2 delta x. So that will look like this when we bring this over. Divided by 2 delta x, and that's equal to our acceleration. Now we can go ahead and plug in our numbers. When we do this though, we got to be a little bit careful. I always put the brackets here to make sure I'm putting this in right. So this is minus 5 squared, because that's our negative 5 is our final velocity, and then minus 28 squared. And then on the bottom, we've got 2 times delta x. Again, they use d here for displacement, so we're going to put in 66 on the bottom. So we just have to be careful to put the brackets in the right place so that we make sure that we're squaring the right numbers. That negative 5, when we're squaring that, it's -5 times -5, so it should end up as a positive number. If you just put -5 squared, what it looks like is, without the brackets, it looks like you're just squaring the 5 and then you're leaving the negative in there. So that's a place where people always make mistakes on this, is not setting that up correctly. So just have to be careful that you're squaring the right terms when you plug this into your calculator. Okay, so we got our acceleration as minus 5.75. We've got acceleration, so that should be units of meters per second squared. So what I like to do for these is just double check and make sure that your answer makes sense. So we had our initial velocity. Let's say that going to the right is positive. And then our final velocity, we ended up going this way in the negative direction. So that means that our acceleration should also be pointing in the same direction that our velocity changed. So we started positive, we ended up negative, so that means that our acceleration should also be negative. And it is, so that looks good. Okay, we got another one here. This time the initial velocity is what we're trying to solve for. We're given the time, we're given the displacement, we're given the acceleration. The thing we were not given is the final velocity, and we're not asked to solve for it. So we can go back and we can look at our list of equations, and there's only one that doesn't have the final velocity, which is this one. Delta x is equal to VIT plus 1/2 AT squared. Okay, so now we're trying to solve for the initial velocity here. So let's bring that 1/2 AT squared over to the other side. Now we want to solve for the initial velocity, so we got to divide by time. So we'll have delta x minus 1/2 AT squared, all divided by t, is equal to initial velocity. We're in SI units here, so we can go ahead and plug everything in. So for that delta x, we're going to use d that they gave us as 310. Acceleration was 2.5. Time was 32. And we'll plug that one in to get our initial velocity. Okay, we got an initial velocity of negative 30.3. Okay, we got another one. Initial velocity is 0, giving us the acceleration, looking for time given the displacement. So same thing with this one, we don't have the final velocity and we are not interested in solving for it. So that means we're going to use the same equation here. Okay, so delta x is initial velocity times time plus 1/2 AT squared. Okay, now this one's going to be a little bit harder because we're trying to solve for the time. So if we just tried to rearrange it the way that we just did, we would run into an issue because we've got time there and we've got time squared over here. So this is going to mess us up a little bit with this. So the way that we can do it for this one is they've given us something to make this a little easier, is that the initial velocity is 0. So usually I recommend that if you have a 0 number that's given as 0, is to just plug that in right away because it's going to make rearranging your equation a lot easier to deal with. So if we plug in this as 0, we're going to get 0 times time, and anything times 0 is equal to 0. So this whole term right here is just going to turn into a 0. So we're going to have delta x is equal to 1/2 AT squared. And now it's going to be a little bit easier to solve for. Okay, so we got 1/2 over here. If we want to get that 1/2 over to the other side, we can multiply both sides by 2. On the right side, 1/2 times 2 is just equal to 1. And we'll get a 2 up top here. Then we want to bring the a over so we can divide by a. 2 delta x over a is equal to t squared. And then we go to square root both sides to get our final equation. So square root of 2 delta x over a. And now we can plug in our numbers here. So delta x, we've got minus 96.3, and our acceleration is negative, so we are okay. So one thing that could have been an issue here is if we had a negative number inside our square root, it's going to give us an error because it's undefined. So if you're trying to plug in a square root and you're getting, your calculator is just giving you an error, it's something to do with the negatives that's messing you up here. With this one, we've got a negative on the top and a negative on the bottom, so we should be okay. Those negatives will cancel out and give us a positive number, and that will work for us. So when I plug this in, I get 4.4 seconds for the answer for that one. Okay, moving on to the next one. We've got one more of these, and similar setup here as the last one, just with different numbers. So initial velocity is also 0, acceleration is actually the same, displacement is a different number, and we're looking for time. So I'm going to cheat a little bit, and I'm going to grab the equation that we just used because it's going to be the exact same equation. So we can go ahead and use that to solve for this. So we can say time is equal to the square root of 2 times delta x over a. So a big part of this section, the kind of 2 skills that you need to learn for this is, first part is just trying to figure out which equation to use. If you use that little trick that we talked about, it'll make things a little bit easier. And then the other part that you'll need to do is the mathy part of this, which is rearranging the equation and plugging your numbers in. That's a really big one as well. So that's kind of the 2 places where people get stuck, is they don't know where to start because they're not sure which equation to use. And then if they know what equation to use, they might not know how to rearrange it to get what they want out of that equation. So even though this might seem a little bit tedious, there's not even a real question here, they're just giving us numbers, it's definitely worth going through and doing a whole bunch of these just to get a handle on those 2 skills. And then once you've got a handle on that, now we can move on to some real questions where we've got to actually solve for some stuff. So this one, we have a car which is accelerating from 50 kilometers an hour to 100 kilometers an hour in 6 seconds. What is the average acceleration in meters per second squared? So the first thing that I'd recommend is converting all of our stuff to meters and seconds. We don't really want to be working in kilometers per hour, so this is where our unit conversion is going to come in. This says it accelerates from this speed to that speed. So from, meaning that that's our initial, is 50 kilometers per hour. So we can go ahead and convert that. We did a whole bunch of unit conversions earlier in this video. I'm going to show you another way that we can do this, which is a little bit of a shortcut. We want to get rid of kilometers per hour and we want meters per second. And 1 meters per second is 3.6 kilometers per hour. So again, you don't have to use this shortcut, but it does make it a little bit faster. When you do these, 13.89, let's say, meters per second. Then we can do the same thing for the other one. Take 110 kilometers per hour and convert that over using our little shortcut. So I would suggest trying it both ways and then just do whatever feels best for you. For me, I try to not memorize as much stuff, so having another number to memorize, this 3.6, sometimes is a bit annoying. So sometimes I'll just do it the long way so I don't have to think so hard about what that number needs to be. The next thing we should do is just write down all the information they gave us. So they told us the time is 6 seconds, and we're looking for the acceleration. The thing that they did not give us is our displacement. So if we go to our list of equations, we're just going to look for the one that does not have displacement in it, which is this one. V final is equal to V initial plus AT. And then we can use this to solve for our acceleration. So we're going to bring the initial velocity over to the left side and then divide by time. I'm going to clear off some space here at the beginning. Then we can plug our numbers in there. So we had V final minus V initial. The big number down here was the final, so 30.56 minus 13.89, and we're going to divide that by time, which was 6 seconds. Okay, plug that in the calculator and that will give us our acceleration. Gives us 2.78. Okay, next one we got motorbike rider traveling at 42 meters per second collides with a haystack and is brought to rest in a distance of 4.3 meters. What's the acceleration while they're being brought to rest? And then how many g's of acceleration is this? Okay, so let's start by writing out what was our givens and what are they asking us to find here. So they said this rider is traveling at 42 meters per second initially, and then they're brought to a rest. So they are initially traveling at 42 meters per second. They're brought to a rest, and so anytime it says rest, that term means that the velocity at that time is equal to 0. So they will end up with a final velocity of 0, and the distance that happened was our 4.3 meters. We're trying to find our acceleration, and we can do our little trick again where we look at these lists, and the time was the one that they didn't ask us about and that we don't care about. So we can go back to our list, find the one that does not have time, and use that to solve for the acceleration. So that's going to be this one, V final squared, V initial squared plus 2a delta x. Okay, so we got that. Now we want the acceleration. So let's bring the initial velocity over. And then divide by delta x and divide by 2. So clear off some space up here. V final squared minus V initial squared divided by 2 delta x. It's going to be our acceleration. And then we can plug in our numbers. So it's going to be 42 squared minus 0 squared, which is just going to be 0. So on the top of that fraction, it's just going to be 42 squared. And then our displacement was 4.3 meters. So let's plug that in and see what we get. 42 squared over 2 times 4.3 is 205.1. We're talking about acceleration, so that's going to be meters per second squared. And, just realized I got this backwards here, we've got final minus initial. Let's fix this. So I was looking at this thinking this doesn't quite make sense. We've got positive acceleration, but we're slowing down, so this should be negative. So let's go back and fix this. The mistake is I got these backwards. It should be 0 minus 42 squared. And if we plug that in the calculator, we'll get the same number, but negative. Okay, so it's worth when you're going through these is just to check your number and just ask yourself, does it make sense? Because you'll be able to catch little mistakes like that as you go. So that's our answer for part A, is this number is our acceleration. For part B, they're asking us how many g's of acceleration is that? So this is kind of a weird term, but basically what it means is 1 g of acceleration is the normal acceleration that we would feel on Earth's surface. So 1 g is equal to 9.8 meters per second squared of acceleration. So we just want to figure out how many multiples of 9.8 is this number that we just got here. So to work this out, we just need to take our 205.1 and divide it by 9.8. And that'll tell us how many g's of acceleration we're working with. So it's kind of an odd unit, but it shows up every once in a while here. So we would write this as 20.9. And to kind of make the units make more sense here, to write this better, you would say, down here we could say our acceleration is equal to minus 205.1 meters per second squared. We could also write this, to write this properly, we could say our acceleration is minus 20.9 g's. And that will give us the same thing. So 20.9 times what the normal acceleration is on Earth. Okay, suppose I drop a rock off a cliff. It hits the water below 8.1 seconds later. What is the height of the cliff, and what will the velocity be just before it hits the water? So any of these projectile ones, and some of these other kinematics ones, it's helpful just to draw a little picture so we can kind of imagine what's going on. This is our cliff, and then we got some water down here. And this says that I drop a rock off a cliff. So it starts off right here initially, and then it's going to fall down here. And when it gets to the bottom, it's going to have some more speed. Picture's going to look something like that. Then we can write out what they gave us and what they're asking us to solve for. So when they say I drop a rock off a cliff, drop implies that they're not throwing it off a cliff with a certain amount of velocity, as they're just holding it and then dropping it. So if you're dropping it, that means that your initial velocity is going to be equal to 0. They told us the time here is 8.1 seconds. They didn't tell us the acceleration, but we know that for any projectiles, any free fall problems, that our acceleration is negative 9.8 meters per second squared. So we're putting negative in here because we're sort of assuming that anything in the positive direction is going to be going up, and our acceleration is going down, so it should be negative. What they asked us to solve for is the height of the cliff, so that's our delta x that we're looking for. Then we're also looking for the velocity just before it hits the water, but if we start with part A, we can solve for delta x. So with that one, we don't have, for part A, we don't have the final velocity yet, and we're not asked to solve for it yet. So we can exclude that from our options of equations, and we can find one that does not have the final velocity, which is this one. Delta x is equal to VIT plus 1/2 AT squared. Now with this one, again, we have the initial velocity as 0, so that's just going to kill both of those terms. Those will go straight to 0. Then we can plug in our other numbers here. So 1/2 negative 9.8, and the time was 8.1 squared. Okay, so let's plug this in and see what we get. 0.5 times negative 9.8 times 8.1 squared gives us negative 321.5 meters. So we got negative here, so let's think about what that means for a second. We said that up is positive, and we got a negative number. So that means that our rock went down from wherever it started from. And that makes sense because we're dropping the rock, so it should be going down. So that's our answer for the first part. Then we need to figure out what is the velocity just before it hits the water. Now when we get to this part, we have a lot more options here. We know more information, so we can really use whatever equation that we want here to work this out, provided that it has the velocity as our option. Sorry, that was delta x. Is that one. We want to find the velocity just before it hits the water. So in this case, I usually just look through the list of equations and figure out whichever one's going to be kind of easier to work with. So for this, I would probably just go final velocity is equal to initial velocity plus acceleration times time. Initial velocity is 0, so we can plug in our numbers here for this. So minus 9.8 and our time of 8.1. And that should give us our final velocity that we can work with. Okay, so minus 9.8 times 8.1 is minus 79.4 meters per second. So again, we got negative because our rock is heading down, and we said that up is positive. So we got a negative answer for our final velocity. That is okay. To answer the first part properly, what's the height of the cliff, you would probably just answer that as a positive number if you're saying what the height of the cliff is, to write it in a proper sentence. But the displacement of the rock is negative because the rock went down. Okay, next up we got a tennis ball at ground level is launched vertically upwards at 19 meters per second. What's the maximum height above the ground reached by the ball? So we've got something like this. Ball starts off down here with some initial speed. It goes up, and then at some point it's going to come back down. So if we look at all these questions, we've got the maximum height above the ground. How long does it take the ball to reach the maximum height? Total flight time, and the impact velocity of the ball. Okay, so the first part that we're interested in is the maximum height. So I'm going to put a little dot up there because that's a point that we're interested in. So for the first part, our initial is going to be down here, and our final is going to be up here. We were given initial velocity as 19. At this final spot up here, this is right when the ball starts to turn around. So just at that instant, it's going to have a final velocity of 0. Then we also know our acceleration. We were given that sort of implicitly. You can imply that it would be negative 9.8 meters per second again. And that's all that we've got. So for part A, we were not given the time, and we're asked to solve for our delta x here. So we can go back to our list of equations, and we'll use the one that does not have time in it, which will be this one. So let me get rid of this and write the equation here. So we want v final squared is equal to v initial squared plus 2a delta x. Then our final is 0, so 0 squared is still 0, so we can replace that with a 0. And now we're solving for delta x. So we can bring that minus vi squared over to the other side, and then divide by 2a. Okay, so we can plug in our numbers. Minus 19 squared. Again, I'm going to square that number first and then apply the negative to it. And then 2 times negative 9.8. Alright, so we're going to plug that in and see what we get. Okay, that gives us 18.4 meters. So that's the height that the ball reaches before it starts turning around and coming back down. So we've got that sorted out for part A. For part B, they want to figure out the time that it's going to take to reach that maximum height. So we can back up here and figure that out. Now we have some more information, so this should make this easier to solve for. We're looking for the time. We've got a lot of information to work with here, so I'm probably going to go with this one again, just because it's a bit of an easier equation to work with. Final velocity at 0. Bring the v initial to the other side, and divide by the acceleration. We can plug in our numbers. Minus vi was 19, or minus 9.8. Okay, so we'll see what that gives us. Minus 19 over minus 9.8. Okay, so that gives us 1.939, let's say, seconds. Okay, so now that we've got that solved for part B, we can start taking a look at part C. So for part C and D, now our information changes here a little bit. What's the impact velocity of the ball? And what's the total flight time of the ball? So now the spot that we're looking at, the final, is kind of moved over here for part C and D. Now we're looking at the final down there. So what we could do is sort of get rid of some of the information that we had here before. So now the initial is still going to be 19. Our final is not going to be 0. So we can get rid of that. That's an unknown. Now we know that for the second part, the total displacement should be 0, because we're starting and we're ending at the same spot. We go up, but then we go back down. So we start and end at the same spot, so that should be 0. We can't use this delta x anymore for the second part, and we're not going to use this part. So we're going to kind of toss those aside because those only apply for parts A and B. So now if we want total flight time of the ball, we know a few things here. We know the initial velocity, we know displacement, we know acceleration. We don't know final velocity, and we want to solve for time. So we can do that here with one of our equations. So we get the equation that does not have time in it, and we can work with that. Delta x is equal to v initial t plus 1/2 at squared. Now our displacement is 0, so we can plug that in as 0. Then we're going to have to do a little bit of math here to kind of sort this out. So on the right side of this equation, we can factor a t out of this. So if we factor t, then that first term becomes vi, because vi times t is what we had before. And then the second term becomes 1/2 at naught squared. So if we multiply those two terms in, we should end up with what we had before. Now this gives us two different solutions. This one equation gives us two different solutions for t. One of the solutions is where this part is equal to 0, and then the other solution is where this part equals to 0. So if we look at the one on the left here first, the one on the left, all that says is that t is equal to 0, which is true. When t is equal to 0, we get a displacement of 0. That is true, but not helpful. So the other equation that gives us is vi plus 1/2 at is equal to 0. That's the one that we want to use to solve for this. So we can bring the vi over to the other side of the equation, and then multiply by 2 and divide by a. So that's minus 2 vi over a. Now we can go ahead and plug in our numbers for that part, and that will solve for our time. Okay, so t is equal to minus 2 vi. Initial speed we had was 19, divided by acceleration, minus 9.8. And let's see what we get for that. Okay, so we have minus 2 times 19 over minus 9.8, which gives us 3.878, let's say. Okay, so that was a whole lot of work to solve for the time. There's a huge shortcut that we could have done here. We said that from the first part, it took 1.939 seconds to get from the initial to the top of the path. Since we're ending up at the same spot at the bottom, it should just be double of what that was. So a big shortcut that we could have done here to skip all these calculations is say that the time that it takes for the total flight should just be double what it takes to get to the top, as long as we start and end at the same height, which we are in this case, so that works for us. So if we double that number, we should get approximately the same thing that we just calculated here, which is 3.878. Gives us the same number. So that's a huge shortcut here, especially for tests. If you can kind of write a sentence or something to say why you're doing it like that, that might be helpful just to get full marks for that one. But yeah, huge shortcut. Okay, so that's the total flight time of the ball, 3.878 seconds. Now we want to find the impact velocity. So again, I always just go with whatever is going to be easiest here. There's also a shortcut for this, which we'll do, but we'll do it the long way here first. We'll say that our impact velocity is initial velocity plus acceleration times time, and we can go ahead and plug in those numbers, 19 plus negative 9.8 times 3.878. We get that final velocity. And we plug that in, we get negative 19 meters per second. So that's the same as our initial velocity, just negative. So that should make sense because all that we did is we just went up and then back down. So we're going up and then back down. We should have the same speed, but now we're moving in the opposite direction. We started going positive, we ended up going negative. So we still have 19 meters per second for our speed, but our velocity is negative because we're going down. Another thing to keep in mind is anytime they say an impact velocity, in all of these questions pretty much, we're talking about right before it hits the ground. So a lot of time people think, what's the speed at impact? Well, you'd say it's 0 because you've hit the ground and you're not moving. But for pretty much all these questions, you're assuming that it's right before it hits the ground. Okay, the next one we've got, a ball is dropped from a height of 215 meters. How much time does it take for the ball to hit the ground, and what is the impact velocity of the ball? So we can draw a little picture here if we'd like. We're starting up here, ending down here, just before we hit the ground. It says the ball is dropped, so we can go ahead and say that that initial speed is 0. What's the impact velocity of the ball? So just before it hits the ground. That's what we're looking for. It was said that it was dropped from a height of 215 meters. So our displacement, we would say we were going down by 215. So that's one that you got to be a little bit careful of because they didn't put a negative in the question, but because we're saying that up is positive, then we've got to put that negative in there to make that work out. We also know our acceleration again is negative 9.8 meters per second squared. And for the first part, we're trying to figure out time, and we don't have final velocity at the beginning. So we're going to go to our list of equations, find the one that does not have final velocity, which looks like this. And the initial velocity is 0, so same thing's going to happen with this one, where that whole thing is just going to turn into 0. And then we can use this to solve for the time. So we've got delta x is equal to 1/2 at squared. Multiply both sides by 2. Divide both sides by a. And then square root both sides. Okay, we can pop our numbers in there. We've got 2 times negative 215 over negative 9.8. Okay, so this is the part where you could run into an issue, is if you didn't put that negative in there, then that means that you would have a negative number underneath the square root, and your calculator would give you an error. So I see this all the time when I'm tutoring students, is they get hung up on this because they forgot to put a negative in there, and they're not getting the right answers. So just have to be careful that we don't miss a negative so that our calculator will let us do that calculation. Okay, so that one I got 6.62 for the answer for seconds. That's how long it takes before it hits the ground. And then for part B, we're going to figure out what is the speed of that ball right before it hits the ground. Okay, so what's the impact velocity of the ball? Let's see what we got here. So we have the acceleration. We know everything except for the final velocity. So again, this gives us more options, but let's just go with the simpler equation. Final velocity is initial plus AT, and no rearranging needed. And also that is 0, so that's easy. So it'll be 0 plus negative 9.8, 6.62 seconds. And we can plug that in to get our final velocity. This is going to come out as a negative number, which again should make sense because it is going down. Negative 64.9 meters per second. What is the rate of acceleration of a mountain bike which slows down from 16 meters per second to 5 meters per second in a time of 3.25 meters or 3.25 seconds? So let's write out what they gave us here. It says it starts at 16, ends at 5. Time it takes is 3.25. We want the acceleration, and we do not care about the displacement. So we're going to find the equation which does not have displacement, which is this one, and we're going to go with that. And we want the acceleration here, so we can bring that final velocity to the left side, and then divide by the time. So our acceleration is going to equal final minus initial, so 5 minus 16 over 3.25. Okay, we'll plug that in. Minus 3.38 meters per second squared. Okay, we got a long one. RCMP officer is investigating a car crash. At the scene of the accident, there are skid marks that are 28.5 meters long. The driver of the car was speaking on a cell phone during the accident, and the cell phone records the sound of the skid for 2.67 seconds. The speed limit on the road was 50 kilometers an hour, and the driver claims that he was not speeding. Calculate how fast the car was driving before the driver hit the brakes, and then figure out if they should be charged with speeding. So this is a classic question. I see this on assignments all the time, sometimes on tests as well. So let's kind of draw a little picture here to kind of figure out what information we have. So the things that we know for sure is that there was a car that was going some certain speed. It slid on its brakes, slammed on the brakes, and then it came to a stop over here where the final velocity was 0. So we're not sure if the initial speed was 50 kilometers an hour or not. That's what we're trying to figure out. So we shouldn't use that as a given to start us off. We'll just leave it as an unknown for now and just figure out how fast the car was going. We know that the displacement, the skid marks, are 28.5 meters, and we know the time that it took to stop was 2.67 seconds. So the first thing that we are not concerned about is the acceleration for part A. So we're going to find an equation which does not have the acceleration and go with that. So this is the one that we haven't used yet, but it looks something like this, that our displacement is 1/2 VI plus V final times T. So we know the V final is 0 in this case, so we can go ahead and plug in that 0 right away. So that'll just turn into delta x is equal to 1/2 V initial times T. We can drop the brackets there as well since there's no addition anymore. Now what we want is the initial time, so we can multiply both sides by 2 and then divide by t to give us that initial speed. Now we can go ahead and plug in our numbers here to get what we need. So that was 2 times 28.5 over 2.67. Plug that in the calculator and see what we get. Alright, so we get 21.3 meters per second. So that was their initial speed before they started hitting the brakes. So that's our answer for the first part. We can leave it like that. Now for part B, they want to figure out if the driver was speeding, but we can't really compare this yet because we have meters per second and the speed limit is in kilometers per hour. So what we've got to do is we've got to convert this over to kilometers per hour. So we're going to take 21.3 meters per second, and let's do this the other way. Let's go like this, meters per second. We'll convert this over to kilometers per hour. So we want to get rid of the meters, get kilometers in there. 1 kilometer is 1,000 meters. Then we want to go seconds to minutes. 1 minute, 60 seconds. And then we want to go minutes to hours. 1 hour, 60 minutes. So now what we can do is plug that in and we'll get an answer in kilometers per hour, and then we can compare that to see if it's higher than 50. So plug that into the calculator. 21.3 divided by 1,000 times 60 gives us 76.7 kilometers per hour. So yes, they were definitely speeding because the speed limit is 50. Okay, next up we got a certain airplane has an acceleration of 16 meters per second squared, assuming it starts from rest. How fast will it be moving 3.2 seconds after it starts down the runway? How far will it travel? And then minimum takeoff speed is 64 meters per second. What length must the runway be? So we can divide this up into some separate sections here. So first of all, we've got our airplane, which starts off from rest, so initial velocity is 0, then goes along the runway, and at some point, at this point, 3.2 seconds has passed. Then I'm assuming later on down the runway, it's going to be moving at a big speed for part C. So we'll leave that part out here for now. Let's just say that this is our initial and final for part A and B. And for parts A and B, we know that the initial velocity is 0, final is unknown, which is what we're trying to solve for. We know the acceleration is 16, and we know the time that it took to get there was 3.2 seconds. So the first part is we don't care about the displacement, we're only looking for that initial velocity. So we can go ahead and grab the equation which does not have displacement in it. So let's go like this. Let's go v final is equal to v initial plus acceleration times time. Initial velocity is 0, we can get rid of that, and we can plug in the information they gave us. So final velocity should be acceleration, 16, time 3.2. So we can plug in our calculator, 16 times 3.2. 51.2. Alright, so that's our initial speed. That's our final speed, sorry. Once we get 3.2 seconds down the runway, now we want to figure out how far it will travel in those 3.2 seconds. So we've got all the same information here to work with, and we just need to figure out what the displacement is. So in this case, we can look at all the equations that we have and just kind of pick whichever one is easiest to work with. So I'm going to go ahead and use that one we were just using recently. The delta x is equal to 1/2 v initial plus v final times t. Now we know the initial is 0, so we can get rid of that, and then we can plug in our numbers here. So the final velocity, we figured that out, was 51.2, and the time was 3.2. So I'll go and plug that in the calculator. 0.5 times 51.2 times 3.2 is 81.92 meters. So those are our answers for part A, and this one was for part B. So we got that answer for A, that answer for B. Now we can go ahead and answer part C. So for part C, we're going to kind of get rid of most of the information here. We're still going to have an initial velocity of 0. Time might be different. Let's leave that like that. So we can go and edit our picture here as well a little bit. So now our final is not going to be after 3.2 seconds. It's going to be way over here, which is when we have that final speed of 64 meters per second. We're trying to figure out the displacement, and we don't care about the time. So we look at the equation. The one that doesn't have time is this one, v final squared, v initial squared, plus 2a delta x, and then we want to rearrange that for delta x. So we can bring the initial speed over to the left side, and then we can divide by 2a. So what we'll end up with, if we divide by 2a, is delta x is equal to v final squared minus v initial squared over 2a. And then we also have a 0 over here, so that whole term is going to disappear from our equation. Now we can go ahead and plug in our numbers and get that displacement. So delta x is equal to our final speed, which was 64 squared, minus 0 squared, we plug that in, and then 2 times the acceleration. It still should be 16 in this case because it just said this acceleration is 16 for the whole runway, so we can go with that. And then we can plug in our number here. So 64 squared minus 0 squared over 2 times 16. That gives us 128 meters. So what length must the runway be? Longer than 128 meters. Okay, next up we got a roller coaster which launches riders from rest to a speed of 89 kilometers per hour in 4 seconds. What's the acceleration and how many G's is this? So you're seeing the G's show up again. So let's write what we've got here. It says from rest, so that means initial speed is 0. And then we've got our final speed of 89 kilometers per hour. We're going to go ahead and convert that to meters per second just to get things started here. So we want to get rid of kilometers per hour. We want meters per second. 1 meters per second is 3.6. So we're using the shortcut again here to work that out. You could do this a long way too. And that is okay. So we get 24.7 meters per second. And then we also know that the time is 4 seconds. That's how long it takes to go from 0 to 24.7 meters per second. Then we can go ahead and solve for our acceleration. We're not interested in the displacement, so we'll find an equation which does not have displacement, which is going to be this one. V final is equal to V initial plus AT. V initial is 0 again, so we can get rid of that. And V final is equal to our acceleration times t. Now we can rearrange that here. So we want to find the acceleration, so we're going to divide both sides by t. So we'll get V final over t. Our V final is 24.7. Time is 4. So we can plug that in to get our answer. So 24.7 divided by 4 gives us 6.175. Going to just round that to 6.2 meters per second squared. So that's our acceleration that we're working with, 6.2 meters per second squared. That's the answer for part A. Now we want to figure out how many G's is this. So this is where we've got to do that thing where we divide by 9.8. So we can take our acceleration as 6.2 divided by 9.8. And if we plug that in, we'll get 0.63. Again, the units for this are G. It's not really a unit, I guess. Write it like this, 0.63 G. Looks a bit awkward because it looks like we're saying grams here, but it's G as in 9.8 meters per second squared. So it's a little bit less than 9.8, so that's why we get a decimal as our answer here. Alright, next up we got a ball thrown straight up with a given velocity, and we got a bunch of questions based off that. So how long does it take for the ball to reach maximum height? What is the maximum height? What's the impact velocity before it hits the ground? And how long is the ball in the air for? So this one looks similar to the one that we did before, but it's a little bit different. We can draw the picture here so we can see what this looks like. So let's say that's our cliff, and it's starting up here, and then it goes up, and then comes down. It's given an initial speed, 46 meters per second, and then the first thing that we're worried about is just this final speed up, or the final up here, which is at the very top. So for part A, we're going to say our initial velocity is 46 meters per second. We're looking at the spot right when it stops and turns around, so we're going to say our final speed is 0. I've sort of drawn this picture like staggered, but in real life it's going up and then coming back down, sort of right on top of itself. But I've drawn it separated a little bit just to make it a bit easier to look at. Okay, what else do we know? Acceleration is negative 9.8 meters per second squared, and we're looking for the time is what we're trying to find, and we don't care about the displacement for the first part. So we're trying to find the time when we don't care about the displacement, so we can go and grab that first equation, which looks like we're going to want this one. V final is V initial plus acceleration times time. V final is 0, plug that in, and then we can rearrange for the time in this case. So we'll have minus V initial is AT, and then divide both sides by A, so that we'll get minus V initial over A for the time. So we'll have minus 46 over minus 9.8, and then we can go and plug that in to get the time it takes to get to the very top here. Alright, so we get 4.69 seconds for that first part. Now we've got to figure out how high does the ball reach. Now this second part, they're not being super specific the way they wrote this out. They're just saying the maximum height that the ball reaches. I'm going to go ahead and assume that what they mean is the maximum height as measured from the ground. So we're going to try and find the height from here to here for part B. So we had from that first part, we had 4.69 seconds, so I'm going to go ahead and leave that in there. Now what we can do is, if we go initial and final, the same setup that we had before, now we're going to try and solve for our delta x in this case. And we got a good equation we can use for that. We got a couple different options here. Let's maybe go with this one. Let's go delta x is equal to 1/2 V initial plus V final times t, and then we've got the final as 0. So we can cross that one out and get rid of it from our equation. Delta x is equal to 1/2 V initial t. Okay, now we got that. Let's go and plug in our numbers. Delta x is equal to 1/2. V initial was 46 meters per second. Time, we figured that out from the first part, 4.69. And then we can figure out our delta x. So 1/2 times 46 times 4.69 gives us 108, let's say, let's round it. So if they're asking for the maximum height from the top of the cliff to the maximum height, our answer would be 108. But if they wanted to know what's the maximum height all the way from the ground to where it stops at the top, then we'd have to add that extra 95 in there for the height of the cliff. So in this question, they're not being very specific. If you're on a test or something like that, I would just double check with your teacher, but maybe I won't call this delta x. But our final answer would be 108 meters plus 95 meters to get us all the way from the ground to the very top. So in some questions, they're a little bit more specific and they'll be a bit more clear with that. But if they're not clear, you can always double check with your teacher to see what they're looking for. Okay, so that's our answer for part B. Now we want to figure out what is the impact velocity of the ball just before it hits the ground. And we're trying to figure out how long the ball is in the air. So let me write this one up here. We're going to move this delta x as 108 meters, just in case we need that. Then let's get rid of all this and figure out what information we have to work with. So for part C and D, now our information is going to change a little bit. Now we've got our final is down here, and we have to change some of these numbers or sort of exclude some of these numbers that aren't going to be helpful for us. So the final velocity of 0, we can sort of get rid of that for now. The time that we got, we can't reuse that number because that's the time to the very top. This delta x also is not very helpful, so maybe let's just get rid of that. Let's see what information we are left with in this case. So if we get rid of all of those, now our new delta x is just the height of the cliff. So we went down by 95 meters, get down to the bottom. So we have that piece of information. We're looking for the final velocity is what we're trying to find here. And we don't have, we're missing something. We don't have the time. So the time's the one that we're missing. So we can go ahead and use this equation here to work that out. V final squared is equal to V initial squared plus 2a times our displacement. So what we can do is we can square root both sides of this equation. And I'm going to do this purposely wrong here for a second so I can show you a really common mistake. So I've already made a mistake. If you know what it is, that is great. But we're square rooting both sides of this equation, so we'll go ahead and plug that in. For our numbers, negative 9.8 for the acceleration, displacement negative 95. And if I go ahead and plug this in like this, I will get 46 square root of 46 squared plus 2 times negative 9.8 times negative 95, which gives me 63 meters per second, approximately. If I look at the answer key says the answer is negative 63, which makes sense because in this case we're going down at the bottom of the cliff. So positive 63 would be like we're going up, and that's not the case. We're going down. So to make sure we get this right, when we do the square root of both sides of this, there's actually a little plus or minus that shows up here. So we get two answers when we square root both sides of the equation. One of them is positive 63, and the other one's negative 63. We have to look at our situation and choose whichever one makes more sense. So in this case, we're going down. It should be negative 63, and that's the answer we get for part C. Now we want to figure out how long the ball is in the air for. I'm going to leave this number over here because we might be able to use it. Now we are looking for the time when we have the final velocity. So now we can go back to our equations. Let's go ahead and use this nice one. V final is V initial plus AT. We've got all the information that we need from here, and we can use that to solve for the time. So we can go V final minus V initial is equal to AT, and then divide both sides by A. V final minus V initial over A, and then we can plug in our numbers. So V final was minus 63, V initial was positive 46, and our acceleration is negative 9.8. So we'll plug that in to get our final answer for this one. Alright, we got 11.1 seconds, and that is how long the ball is in the air for the whole flight. So from where it starts from, all the way to the top, and then all the way back down to the ground. Alright, so now we got a ball that is thrown straight down from a cliff with a velocity of 30 meters per second, and they give us the height of the cliff. So let's draw this out. We've got an initial velocity this time, which looks like that. We'll say we're going down, so we'll say minus 30 meters per second. I can draw my little positive over here. And then a little bit later we'll be down here, and we'll be going even faster, but we're not sure what that speed is yet. That's what we're trying to solve for. And the displacement that they gave us is also negative, 195 meters. And then we got our acceleration as negative 9.8 meters per second squared. So when I do these, I usually just put up as positive and down as negative every single time. You don't have to do it like that. So if you see someone else solving these questions and they've done this a little different where they put down as positive, that still works. You'll still get the same answers. It's just positive will mean down instead of up. So don't panic if you see it done a different way. There are definitely more than one way to set these ones up. So once we got this, now let's figure out what are we missing here. We don't have the time and we don't want it, but we do want our final velocity. So we can go to our equations, find one that has final velocity and not time, which looks like this is going to be the one. Okay, so now we're using this equation. Let's do this properly this time and not make any mistakes. So when we go ahead and square root both sides of the equation, we're going to go v final is equal to plus or minus square root of all of this stuff. So v initial was negative 30 squared. I'm going to make sure to square the negative when I do that as well, because this should turn out as a positive number, plus 2 times negative 9.8 times negative 195. If I plug it in like that, I should be okay. We're going to get plus or minus for our answers here, and then we know for this case we're going down, so we're going to want to take the negative solution. So we're going to put a negative outside of our square root sign when we go and plug this in. And we'll plug in the numbers that we got. And I get negative 68.7 meters per second. All right, we're moving on to the forces questions. So here's the first one we got. Net force acts on a 2 kilogram mass and it gives an acceleration of 3 meters per second squared. How large is the force? And then a couple other questions for part B, but let's start with that one. How large is the force? So let's write out our equation here first and just see what we can do with this. So this is our Newton's second law, which says that our net forces should be equal to our mass times acceleration. So before we actually solve this, let's just talk about this for a second. That net just means the sum of. So we're adding up all of our forces on the object. So when we write F net, it could be that there's no forces there. There could be a bunch of different forces and we're all adding them together. So we'll write F net, which just means that for this situation that we're working with, we're just going to add up all the forces. So for this question, it just says that the net force acts on an object and gives it the acceleration. So we were given everything we need to just plug in this equation. F net is equal to 2 kilogram mass times 3 meters per second squared, and that will give us 6 newtons. So you can look at the units here. The units are a little bit weird, but we had kilograms for mass and meters per second squared. As long as those are the units for mass and acceleration, we'll end up with newtons as our force. For part B, we're looking for the acceleration when we have the same force acting on an object, but the object's mass is different. So now we're still going to use 6 for the net force, but we're going to change the mass. So we'll go F net is equal to mass times acceleration. Now we want to solve for the acceleration, so we've got to divide both sides by the mass. So we'll get F net over mass. And we go and plug that in. So we had 6 newtons. Now we've got 1 kilogram of mass. So 6 divided by 1 is 6 meters per second squared. So now we're going to do the same thing with a different mass of 4 kilograms. So we're going to use the same equation here, same setup, is our F net over our mass, but now our mass is going to change. So we're still going to have 6 newtons of force, but the mass is changed to 4 kilograms. So that's going to be 1.5 meters per second squared. Okay, so the main takeaway from this question is that if we change the mass of our object, it's going to change the acceleration. So if we have a really light object, we're applying the same force to a light object, kind of medium weight object, and heavy object, the acceleration is going to be different, which should make sense intuitively. If something's really big and you're pushing on it, or something's really small and you're pushing on it, you're going to have a different acceleration. Let's move on to the next one. An 800 Newton person stands on a scale on the floor of an elevator. What is the scale reading if the elevator has an acceleration of, and then it gives a few different options. So let's draw a little picture here to see what's going on. So we've got a person who's standing on a scale, and then the scale is reading a certain measurement. So if we think about what the scale is experiencing, the scale has some sort of force like this, 800 newtons, and that's the force that the scale feels. Then the scale is sitting on an elevator, and the elevator is kind of pushing up on the scale. So this is like the floor of the elevator right here. And then we also know that in the first part, the elevator is moving up by 2 meters per second squared. So that's the acceleration that they gave us for the first part. So this is kind of like our unknown force, I guess, in this case. So let's figure out how to put this together in Newton's second law. So let's think about what we need to deal with in this equation. So let's start with this. 800 Newton person stands on the scale. So that means that the force of gravity from that person is 800 newtons, but we also know that the force of gravity is equal to m times g. So they actually gave us the weight of this person, they did not give us the mass of this person. So the first thing that we should do is just solve for the mass of the person. We have 800 newtons is equal to the mass times g, which is 9.8. We can divide both sides by 9.8 to get the mass of the person. So let's start with that, which gives us 81.6 kilograms. So that's the mass of our person, first of all. Then let's use our Newton's second law to see how we can sort this out. So we have F net is equal to mass times acceleration. In this case, in the F net, we have two different forces. We have that unknown force, which we just called F in this case, and then 800. If we assume that positive is up, then F I'm writing as a positive number because it's going up. 800 is pointing the other way. It's pointing down. So we're going to use that as a negative number on here. Then the M, the mass, we know that is 81.6. And then the acceleration, it says the acceleration is also going up. So that would be positive 2 that we can plug in there. And then with this, we can bring that 800 over to the other side as a positive number. And now we have everything that we need to plug in and solve for what that force is. So this unknown force, this is what the scale is going to be reading. So it would be 800 plus 81.6 times 2, which is 963.2 newtons. Okay, so the way you kind of picture this physically is imagine that you're standing in an elevator and the elevator is going up and it's accelerating when it's going up. Then it's going to feel like the scale has more weight on it than it does because of that acceleration. So you can kind of feel it in your feet when the elevator accelerates quickly. That's this number here. It's more than what your normal weight is because you're accelerating up. So now there's a few different parts to this, B and C, and most of this is going to be exactly the same. There's just going to be a little bit that's different. So let's get rid of all these calculations here. The only thing we really need is we need that mass, 81.6. That's going to stay the same. All of this is going to stay the same, except for this last part here, because now it says that it's 2 meters per second squared going down. So now our acceleration is going down, so it's going to be negative. So we'll end up with almost the same thing here. It's going to be 800 plus 81.6 times negative 2 now. So now the scale is going to read a little bit less than your normal weight because you're going down. So it's going to be 636.8 newtons. Okay, now the very last one is we're going down at exactly 9.8 meters per second squared. So let's see how that will change things. We're going to get a bit of a weird result here, but we'll plug it in and we'll see what we get. So now everything's the same, but our acceleration is negative 9.8. So if we plug that in, we'll see what we get here. 800 plus 81.6 times negative 9.8. If we plug that in, we get pretty much 0. So we're going to just round this to 0. So this would be the acceleration that the elevator would have to go in for the scale to not feel any force at all. So it's accelerating at exactly the right speed. It's 9.8, which is our number that we use for G. So the scale at this point is feeling nothing. And you would feel like you're sort of floating at this point. All right, a cord passing over a frictionless pulley has 4 kilograms for the mass. And then we've got another mass on the other side, 12 kilograms. Find the acceleration of the two masses and the tension in the cord. So for these types of problems, when we have pulleys, we've got two different masses. And anytime we have two different masses, that means that we are probably going to have two different free body diagrams that we need to worry about. So let's do a free body diagram of mass number 1. And instead of drawing this like a box, I usually just draw it as a dot. Makes things a little bit easier. Mass number 1 has got its own force of gravity on there. And then there's going to be the tension from the rope pulling upwards. Mass number 1 is light. Mass number 2 is heavy. So the acceleration on mass number 1 is going to be going upwards in this case. And we're going to call this T for tension. Then we can do the same thing for free body diagram number 2. Draw it as a dot. It's got its own force of gravity going down. I'm putting FG1 and FG2 because those will be different numbers. And then it also has a tension going up. So the thing to keep in mind here for these pulley questions is that the tension in the rope is the same. We don't need to write tension 1 and tension 2 here and solve for both tensions because they're both going to be the same number. So we're going to drop the 1 and 2 and just write T. It's just the same tension. This one is going to be moving down, so it's going to be going like that, and that's going to be our acceleration. Same with the acceleration, as long as an object is rigidly connected to another object, which with a pulley that would be the case, the accelerations are both going to be the same value. They're going to be pointing in different directions, but they're going to be the same value. Now we want to find the acceleration and the tension in the chord. So the tools that we have to work with here are Newton's second law. So we can write out our F net is equal to ma for both of these free body diagrams. So let's do the one on the left here first. Tension's going up, so that's going to be positive. Force of gravity 1 is going down. So instead of force of gravity 1, I'm going to write m times g. And then on the right side here, the acceleration is going up, so I'm going to leave this as positive. The mass that we're talking about is mass number 1 in this case, and the acceleration like that. Okay, so we look at this equation, we got two unknowns, we got the tension and the acceleration. That makes this awkward to solve. We can't solve for this right away. So we've got to do the same thing but for the other mass over here. So for this one it's going to look similar. It's going to be tension minus force of gravity 2, which is m2g. And then this one our acceleration is going down, so we're going to go minus here. We're going to put a minus because that acceleration is a negative. So acceleration is going down, so we're going to put a negative over there. All right, now we got two equations, two unknowns, so we should be able to solve this. So what we got to do is substitute some things in here. So let's take our equation on the left and let's rearrange it like this. Let's bring the mass over to the other side. m1g plus m1a. And then we can take that tension equation and plug it in there. So instead of tension, we're going to substitute m1g plus m1a minus m2g equal to minus m2a. So we've replaced tension with what we had for the other equation there. And now we can go and solve for the acceleration. So I'm going to bring all the terms that have acceleration over to the left side, and all the terms that do not have acceleration over to the right side. Okay, now I'm going to get rid of some stuff over here because we don't really need it. I'll get rid of all this. Clear some space out. So we want to solve for the acceleration, so we've got to factor it out of that first term on the left side. So that's going to be acceleration times m1 plus m2. And then on the right side, we could factor out g as well if we want to, totally optional, but make our equation a little cleaner. So we'll factor out a g out of that. And now we want acceleration by itself, so we're going to divide by m1 and m2. So we're going to get it g and let's see here, I think I got a mistake in here because we're getting some weird results. Yeah, one of these should be minus. Okay, here was the mistake. Let's fix this. So m1g, when we brought this over, it was positive. So when we bring it over, it should be negative. So there should be a little negative in there. And that would make a little negative in front of my m1 over here. Okay, there we go. Now I'm going to get rid of these and this. I'm going to leave that top equation there because I'm going to need it here in a second. But let's plug in our numbers here. Negative 9.8, and then the masses we have minus 4 plus 12, and then 4 plus 12. So let's plug that in, and then we'll get our acceleration. And we can go from there. Alright, so that gives us 4.9 meters per second squared. Let's check that answer before we get too carried away here. 4.9 meters per second squared. Okay, that looks good. So now let's go and do the tension. So the only thing I need from this is I need to just keep that 4.9 meters per second squared number handy. I'm going to get rid of all this gross algebra, and we're going to go back to this equation that I left behind here. So we want to solve for the tension, and now we have enough information to do so. So I'm going to bring the m2g over to the other side, and then we can plug in the acceleration here. And let's actually factor this as well. Let's go m2 g minus a. And now let's plug in our numbers. Alright, so we had m2, which was 12. Acceleration, which was 4.9. So we'll plug that in, and we'll get a value for that tension. 58.8. Okay, if a force of 270 newtons is required to start a 40 kilogram box moving across a concrete floor with constant velocity, what's the coefficient of friction between the box and the floor? So let's draw a little picture. We've got a box sitting on the floor. Then let's draw some forces on here. So we're applying a force, call that FA, usually as an applied force, of 270 newtons. 40 kilogram box is going to have its own force of gravity. It's sitting on the floor, so it's going to have a normal force. And then it is kind of being dragged along the floor here, so it's going to have a friction force. Sometimes people will draw this sort of between the connection of the floor and the ground, but I'm representing this box by a dot, so I'm just going to put it right here, because it'll be the same for our equations. So now this is something we haven't gone through here yet, but now we have forces that are going in different directions. So some of them are going in the horizontal direction, some of them are going in the vertical direction, so that's something that we're going to have to take care of when we sort this out. The other part that they told us is constant velocity. So that constant velocity means that our acceleration is equal to 0 in the x direction. It's also equal to 0 in the y direction because we're not moving up or down off the ground or anything like that. But that constant velocity means the x direction acceleration is going to be equal to 0. So now, instead of using Newton's second law where we say F net is equal to mass times acceleration, we're just going to say that F net is equal to 0. That's going to be our Newton's first law. Our goal here is to figure out the coefficient of friction between the floor and the box. So the other equation we're going to have to use to sort that out is that our friction force is going to be our coefficient of friction times our normal force. It's usually an equation that's on a formula sheet that we can use. For this one, we're going to need to solve for the normal force before we can figure out what that coefficient is. So what we can do is we can say F net in the y direction is equal to 0. So we're doing the y as an up and down like this, and x as our horizontal like that. And those are our positive orientations for both of those. So for the y direction, we would have Fn, or normal force, going up minus the force of gravity equal to 0. Equal to 0 because there's no acceleration. Then the normal force is equal to the force of gravity, and the other equation that we have to work with is that our force of gravity is equal to mg. So that means that in this case our normal force is equal to mg. Sometimes people jump ahead a little bit and they use normal force is equal to mg, and they just keep using that as an equation, but you have to be careful because it's not always equal to mg. It depends on the question. So at this point we could plug in our numbers if we wanted to here and just solve for that normal force. So we got 40 kilograms times 9.8. So I'm going to go and plug that in just to get a number for that. So that is 392 newtons for our normal force. Now we can go and do the same thing but in the x direction and solve that equation. So I'm going to leave this number down here, that's our normal force, as 392. So let's go like this. Sum of forces in the x direction. So now Fa is going to be positive because that's going to the right. Force of friction is negative, so that's going to the left. and moving at constant velocity, so we can say the sum of those forces should be equal to 0. The applied force they gave us was 270, we know the number for that. The friction force, we can use the equation that we have over here. And we know that normal force as 392, so we can use that as well. Now we just got to rearrange for the coefficient of friction. So let's go like this. Let's go 270 is, that symbol's called mu. And then we can just divide that over. 270 divided by 392 is equal to that coefficient. And let's go ahead and plug that in. Get 0.69. And that number is unitless. There's no units with that. So that is our final answer for that one. Okay, we've got a sled pulled across sidewalk at constant speed. Horizontal force is equal to that to keep it moving. What's the coefficient of friction? Okay, so similar question. Let's see if we can do this a little faster. Let's do our free body diagram. I'm going to draw this as a dot this time because that's how I like to do it normally. They said a 52 Newton sled, so that means that the force of gravity, Fg, is 52 newtons. We've got horizontal force of 36 newtons, that's our applied force, and we're trying to solve for our friction force. Okay, so to do this a little faster, let's go F net in the y is equal to 0, Fn minus Fg is equal to 0. We're not going to put an mg here because we actually know what Fg is, but our normal force is equal to the force of gravity, and our normal force is equal to 52 newtons. So we got that right off the bat. Normal force is 52 newtons. Now we can go ahead and look at the x direction to sort out that one. So F net in the x direction is equal to 0. Applied force minus friction force is equal to 0. Applied force minus mu Fn is equal to 0. Then we can go ahead and rearrange for that coefficient of friction. So that's going to be the applied force divided by the normal force is equal to mu. And we got that normal force as 52 newtons. So we're going to have 36 newtons divided by 52 newtons. This also kind of shows how the units will cancel out here. It's newtons divided by newtons. So that's why we don't end up with any units here, because they just cancel out. And we get the exact same answer, 0.69. Okay, so just kind of a fluke that happens to be the case. That's alright. Let's move on to the next one. A 4,500 kilogram helicopter accelerates upwards at 2 meters per second squared. What lift force is exerted by the air on the rotors? So for all these force questions, I always just start with a free body diagram because that will tell us how we write our equations. We've got a helicopter with force of gravity going down, and they told us the mass there, so we could work that out and figure out what the value of that is. It tells us that there's a lift force exerted by the air. The other reason that we know that there has to be another force going up is because of that F net equation. Let's say for a second, let me get rid of this force. Let me say for a second that we just had this acceleration going up like this. We know that the sum of forces has to equal the acceleration. So if our acceleration is going up, that means that there needs to be a force here which is bigger than the force of gravity, and that's what's going to be lifting us up. They told us that in the question, but the F net equation also gives us some good information about that. So F net is equal to mass times acceleration. The two forces that we have to work with is this lift force in the positive direction because it's up, force of gravity is going down, so we're going to write that as negative, and we'll write it like that. Now the force of gravity, that's just m times g, and we're looking for that, what we called F there, so we can bring mg to the other side of the equation. So it's going to be mg plus ma, and now we've got everything that we need here. So 4,500 times 9.8 plus 4,500 times 2 for the acceleration, and that'll give us our lift force. So I'll go ahead and plug this into the calculator to get that answer. Okay, so it's huge force, 53100 newtons. Okay, we've got a 20 kilogram box is pulled to the right with an applied force of 100 newtons. It just starts to move. That is, the maximum force of the static friction is 100 newtons. Okay, what is the value of the coefficient of friction? Assume the box is moving at constant velocity. Okay, so let's draw this box that we have with the free body diagram. Let's draw it like this, as a dot. 20 kilogram box, so that means there's going to be a force of gravity based on that. The box is sitting on the ground, because in real life it looks like this. So there's going to be a normal force going up as well. Then it's being pulled to the right with an applied force, and they told us that was 100 newtons. Then they also told us that there's a friction force going back at 100 newtons. What is the value of the coefficient of friction? So, similar setup here. This one, they just kind of gave us the information in a different order, but that's okay. So, same as before, we can solve for what the normal force would have to be. In this case, the only forces going up and down are the normal force and the force of gravity, and we're sitting on a totally flat surface. So we're going to end up with that same result that we had before, where the normal force is going to be equal to the force of gravity, which is going to be equal to mg. So I'm just going to leave it like that for a second, and then we can substitute it into our other equation, where we go F net in the x direction is equal to 0. And you know what, we actually don't really need that one, because we've already kind of solved that that should be 100 newtons. So what we can go ahead and do is just go like this. Friction force is equal to mu Fn, and then we can sub this in here. So friction force is equal to mu mg, and then we can rearrange this to get mu is equal to friction force over mg. Alright, now we got what we need to plug in all of our numbers here. So I'm doing this one a little faster because it's pretty similar to the one that we just did. But feel free to pause this and go at your own pace. Now let's see what we got here. We're going to get a weird number. .51. Alright. Now this one looks similar, but it's a little bit different. We got a box being pulled to the right. If it's accelerating at 2 meters per second squared, what's the value of the coefficient of friction? So now we don't have a constant velocity. Our velocity is changing because we have acceleration. So that's going to add a little bit of complication to this. We've got an applied force as 20 newtons. Now we can't say that this friction force is equal to 20 newtons. It won't be, because we have acceleration. We're still going to have a force of gravity going down. We're going to have a normal force going up. Now that we've got all those, we can go ahead and start solving for stuff. So again, I'm going to skip this a little bit because we did this quite a few times, but the sum of forces in our y direction, our F net, is going to be equal to 0. We'll get the same result that we did before, which is that the normal force is equal to mg. Now that we've got that, we can go and do the net forces in the x direction. This is the part we have to be careful of. This is not equal to 0 anymore. It's equal to mass times acceleration in the x direction. So that's a common place where people make mistakes is to accidentally put the 0 in when it should not be 0, or they put the mass times acceleration in when it should be 0. So now that we've got that, we can say that our applied force minus our friction force is equal to mass times acceleration. And that friction force, we know that should be mu times Fn. We also know that the normal force is equal to mg. So I put mg over here, it should be ma. So if we sub all that in, we get that the applied force minus mu mg is equal to ma. And now we can rearrange this and solve for that coefficient. So let's bring that over to the other side. Swap some things around. So let's bring the mass times acceleration over to the left. Let's bring mu mg over to the right. And then divide both sides by mg. So we'll get that the applied force minus ma over mg is equal to that coefficient. And now this is where we can go ahead and plug in those numbers to get our answer. So that applied force was 20, mass was 5, acceleration was 2, over 5 times 9.8. Alright, I'll plug that in and that'll give us our answer for that part. .2. Okay, let's see what we got for the next one. Alright, nice and easy one. What is the net force required to accelerate a 1,500 kilogram race car at 15 meters per second squared? So that's just a straight up F net is equal to ma. The net force on here, so we can't really draw a free body diagram here because the free body diagram shows all the individual forces, but all we're trying to solve for is the net force. So we can skip right over that and just go ahead and plug it into this equation. Mass is 1,500, and our acceleration is 15 meters per second squared. So we can fire that in the calculator and get our answer for that part. It's going to be a big number, 22500. Okay, next. A rocket which weighs 9,650 newtons on Earth is launched. The force of propulsion is 13,400 newtons. Determine the mass of the rocket, the upward acceleration, the velocity of the rocket at the end of 25 seconds. So this one, let's draw a little picture for this. We draw it over here, FBD. We've got our weight of our rocket, so that's our FG. So not the mass, but the weight is 9,650 newtons. Force of propulsion, so that's going to be like a force that's going up in this case. So we'll just say that's like an applied force. 13400 newtons. Now we want to figure out the mass of the rocket. Okay, so for the mass of the rocket, we can start with our force of gravity is equal to mass times g. We know the force of gravity is 9,650, and we know g is 9.8. So we can divide Fg by g to get the mass. So it'll be 9,650 divided by 9.8. And we'll plug that in to get our number there. So that's 984.7, let's say, kilograms. Okay, so that's the mass of our rocket. That's our answer for part A. I'm going to leave that one behind and move on to the next part. Now we want to figure out the upward acceleration of the rocket. So from our free body diagram, we know that this acceleration should be going upwards in here. And then we can go F net is equal to mass times acceleration. Anything up is going to be positive, anything down is going to be negative. we had to solve that mass from the first part so that we can plug it in here. If they didn't ask us to do part A first, we still would have needed to solve for the mass before we could have done this. So they made this a little bit easier for us by breaking this up into separate parts. Now, we want to find the acceleration from this equation, so we just have to divide by the mass. Okay, and then let me write up my numbers here as well. Do 13400 minus 9650 over the mass of 984.7. That's going to give us our acceleration. Nope, made a mistake there. I got a negative number, which doesn't make sense. I got a positive number now, so that looks better. 3.8 meters per second squared. Let's check our answers here, make sure we're doing this right. Yeah, looks good so far. Now we want to find the velocity of the rocket at the end of 25 seconds. Okay, so this is where it starts to get a little bit tricky because now we're kind of mixing topics together. So now we're not only dealing with forces, but now we're dealing with the final velocity of the rocket. So this is where we're going to have to combine the equations that we were using in the last section with the equations that we're using from this section. So the thing to keep in mind is that the bridge between those two topics is the acceleration. Once we know the acceleration, we can use the acceleration in our kinematics equations, or we can use the acceleration in our sum of forces equations. So they're kind of leading us towards that by giving us part B before we do part C. They're telling you find the acceleration first from Newton's second law, then you can bring that into kinematics and use that to solve those types of questions. So now we got to go back to our kinematics equations and figure out what we've got to start with. They said this thing is launched, which is a little bit vague, but we can say that that is the initial velocity of 0. Final velocity is what we're solving for. We know the time as 25 seconds. Displacement is unknown and not wanting to be known. And then we know the acceleration was the number that we solved for in the last part of 3.8 meters per second squared. So we can go back to our kinematics equations. We'll take a look. We want final velocity without displacement, so it's going to be this one right here. Final velocity is initial velocity plus AT, and then we can just go and plug in the numbers that they gave us. 0, and this one that we solved for, 3.8, 25 seconds. I'll plug that in to get our answer here. 95 meters per second. Calculate the net force that a pitcher exerts on a baseball whose mass is 0.15 kilograms if the acceleration is 225 meters per second squared. So they gave us mass as 0.15 kilograms, acceleration as 225 meters per second squared, and again they're just looking for the net force. They didn't give us any information about the individual forces that are going on in here, so our only option to work with is not to use a free body diagram, but to just go ahead and use Newton's second law. F net is equal to ma. We've got what we need, so we can plug in the numbers. Mass is 0.15, acceleration as 225, and we can solve for this net force. So it's going to be a decently big force, even though the mass is tiny, because the acceleration is pretty big. So we still end up with, well, it's still pretty small, but 33.7 newtons for our answer for that one. What net acceleration would be given to a 9 kilogram bowling ball being thrown with a propelling force of 180 newtons? So they said a propelling force here, but for this purposes, let's just assume that this is the net force that's on here. So we can go ahead and use the same equation that we've been working with, which is that the net force is equal to mass times acceleration, and we're looking for the acceleration in this case, so if we divide that by the mass, we'll get an equation for acceleration. The F net was 180 newtons, and the mass was 9 kilograms, so we should just end up with 20 meters per second squared for that acceleration. Okay, same setup, but now we're solving for the mass this time. We've got F net is equal to mass times acceleration. They gave us the F net, they gave us the acceleration. We want the mass, so let's divide by the acceleration. F net over A is equal to mass. F net was 127.8 newtons, and our acceleration was 9.3 meters per second squared. So I'm just going to go and plug that in the calculator. And we'll work this one out as 13.7 kilograms. Nice and easy.